I'm Lindley, and today I'm presenting on topological data analysis for psychological text data. So basically, this is the methodology of my dissertation, and it's looking at new ways of analyzing text data. So psychopathology is often studying using numbers like scores on a scale or symptom counts, but a lot of what we actually care about shows up in language. So that's how people describe their thoughts, feelings, and behaviors. In this talk, I introduce a new way of approaching text. So by combining text embeddings with topological data analysis, we can start to look at the shape of these texts. So instead of focusing on individual words or features, we analyze the structure of text as a whole, and in doing so, we take a step towards a new topological psychometrics. So like I mentioned on the previous slide, psychology has traditionally prioritized numeric data, even though people express much of their psychological experience through language. So every day we're using text. We're talking in speech, we're writing emails, we're writing texts. Our language is how we typically express how we feel. So classical psychometrics translates unobserved traits such as depression or psychosis into measurable scores. And this is effective. It's served us well for decades, but this approach may sacrifice some of the complexity of lived experience for ease of analysis. So in the age of technology we're in with smartphones, large language models, and text embeddings, this now makes language data easier to collect and analyze. However, embeddings are not just simple scores. They create high-dimensional spaces in which psychological expression can form clusters, gaps, loops, and trajectories. So, for example, if you're looking at like the Quen embedding method, that's almost 3,000 dimensions. So it's not just a simple one numeral score, it's a 3,000 dimensional space. So we therefore introduced topological psychometrics, a complementary framework to classical psychometrics that examines the shape and structure of psychological data. We use psychosis language disturbances as a test case to apply topological data analysis to determine whether distinct disruptions in thought and language produce meaningful different shapes in text embedding space. And I want to emphasize this isn't just about psychosis. This is a general use method to form a topological psychometrics. So this is the outline of the talk. First, I'll give a very brief overview of text embeddings. Then I'll go over the methods of topological data analysis, or TDA. Then I'll give a review of different types of psychometrics like numeric, textual, and topological. And then there isn't really available data set for this analysis, so I generated the text via large language models, and I'll review how that was done. And then I'll get into future analyses for topological psychometrics. So embeddings are basically a way to turn text into numbers that models can actually work with. They take words, sentences, or even whole documents and map them onto points in high-dimensional space. And in this embedding space, similar meanings are meant to end up closer together. So instead of just counting words like traditional methods of text analysis did, we're actually capturing meaning and context. And that's what allows us to take this really messy, unstructured text data and turn it into structured data that we can use in statistical models. Okay, so this is the bones of the talk here. This is topological data analysis, and it's the method that I'm using to analyze the text data. So I'll apply the methods of topological data analysis to text data in order to make comparisons between psychosis language patterns, and I'm going to summarize those methods here. So the most basic unit in TDA is the point cloud, which represents data as points in a high-dimensional space. TDA treats collections of observations as a shape rather than just a set of independent numbers. So in the example I'm going to use today, we have 500 texts. So that means there's 500 points in the high-dimensional space. And I'm using the Quen embedding method. So that means I have 2,559 dimensions in the embedding space. So what this does is it allows us to transform the complex, messy data into a geometric object that can be analyzed structurally. Homology is the basis of TDA. It's the study of where holes are within the point cloud. So TDA works in terms of these homologies, which you can consider them as kind of analogous to like a summary statistic, like a mean or a standard deviation. If you're familiar with network analysis, they're more analogous to a network statistic. So homologies are summaries of what the shape is, how many components, how many connections, and how many loops. And these features tell us about the underlying shape of the data without needing to visualize every dimension. So again, on the previous slide, we had almost 3,000 dimensions. We're not going to look at all of those dimensions. We're going to summarize them into just a few dimensions. So in theory, you can do every dimension if you really wanted to, but in practice, most analyses focus on lower dimensional features like 0, 1, and 2, because higher dimensional structures are computationally expensive to compute. But there is an issue with point clouds in that, unlike with a geometric shape where we have both points and edges already defined, a point cloud has no edges natively. So we need to make a point cloud a shape in some way. And that corresponds to connecting points together. But, that process is totally arbitrary because there's near infinite number of ways you can connect points together to turn it into a shape. One principle here, which is that points that are closer together are assumed to be more similar to one another, which makes it intuitively useful to connect points close together. And this method within TDA is called filtration. So there are two main types of filtration in TDA, Vitors-Rips and check. So in Vitors-Rips, you start with a distance threshold epsilon, and you connect nearby points and form higher dimensional shapes as you increase that distance threshold and more points become connected. So again, as you increase the threshold, clusters and loops appear and disappear, or in literature, that means that they're born and they die. And you track these changes using a persistent homology, which is graphed on a persistence diagram. The check filtration works similarly, except you start with a ball around each data point, which is of radius epsilon, and then you gradually grow the balls or the radius epsilon to connect points when balls overlap. And again, as you increase the threshold, the clusters and loops appear or disappear, or born and they die, and you track the changes using a persistent homology. So the main difference between check filtration and Vitors-Rips filtration is that check filtration is the true topology of the system, where Vitors-Rips is the approximate topology of the system. But the reason that not everyone is doing check filtration all the time is because it's super, super, super computationally expensive. So it's easier just to do the Vitors-Rips. So Betty numbers provide a way to quantify homology. They tell us how many connected components, loops, or cavities are present in a data set. This allows us to reduce a high-dimensional shape into a small number of meaningful summaries, and as the geometric features change with the threshold, so too do the Betty numbers. Okay, so this is the data we'll be using today. So there's 468 Reddit data science examples asking about applying to graduate school, and 468 examples from mental health subreddits of users writing about their plans to commit suicide. And these really are explicit plans that people have left on Reddit. And so obviously we would expect a difference between these texts between people just asking about graduate school and people writing about suicide, but we're going to see if TDA can detect those differences. So we're using the Qwen3 embedding model here. In the dissertation, I used 4 different embedding models, and I just chose this for the sake of example. It's not better or worse than any of the examples. It's just the one that was chosen here. And I'll be using the TDA stats R package and my own functions. So these are the graphs that resulted from the analysis. So on the top, you have the data science Betty diagram on the left and the suicidality diagram on the right. The x-axis is epsilon and the y-axis is the Betty number. On the bottom, you have the persistence diagram for data science on the left and the suicidality on the right. The x-axis is when the feature was born and the y-axis is when it died as a function of epsilon. And the distance from that diagonal line is called the persistence. Pink is 0 dimension, gray is 1 dimension, and black is 2 dimensions. So looking at the graphs, you can see with the Betty diagrams, they're very, very, very similar. Maybe the second, third, and fourth points are a little bit different. But I think looking at that, you might not be able to say like, yes, definitively, there's a difference between these texts. Also looking at the bottom of the persistence diagrams, again, they look very, very similar, but you can see that there is a difference in the 0 dimension on the left-hand side of the graph, where the data science examples persist a little longer. So again, with those graphs, it wasn't super apparent that, yes, there is a difference here, but you can have a quantity that you discover that can tell you if there's a difference. And that's non-Euclidean distances like Wasserstein and bottleneck. So bottleneck distance measures the largest mismatch between diagrams. It focuses on worst case difference. So it finds the points that are farthest apart, and that's the distance it looks at. Wasserstein captures the global distance. And how that global distance is cashed out is in terms of the p parameter. So if p equals 1, it's the average distance. If p equals 2, it emphasizes larger differences. And as p approaches infinity, it approaches bottleneck. So these distances compare topology across all epsilon simultaneously because every feature's lifespan depends on epsilon. So this is the results of the analysis where I have the Wasserstein distance comparing the data science examples to the suicidality examples. So as you can see in the 0 and 1 dimension, there is a significant difference. And so TDA was able to detect a difference between the texts. Okay, but why am I using TDA at all? So psychological data, especially text, is messy, high-dimensional, and constantly changing. But most of our statistical tools are really built for clean numeric data, and they tend to struggle in these settings. But the idea behind TDA is to shift how we think about the problem. Instead, focusing on individual variables, we look at the shape of the data. And by doing that, we can handle high-dimensional structure more naturally and capture patterns that might otherwise be missed. And this opens the door for a lot of things like identifying meaning in text, looking at anomaly detection, and even looking at phase transitions. Okay, so that was the summary of topological data analysis. So let's look at what psychometrics is. So in psychology, methodologists have long appealed to numeric psychometrics as a way to evaluate psychological phenomena. In the age of large language models, I argue that we need to adapt our psychometric methods to new modes of data like text data. So to review numeric psychometrics, classical psychometrics represents unobservable psychological constructs such as depression or personality using numeric responses from questionnaires or rating scales. Statistical models then separate the construct of interest from measurement error and evaluate reliability and validity. And these numeric data are useful because they are concise, standardized, comparable, and compatible with established statistical methods. But there are limitations. So again, numeric measures are useful, but they can create a contextual black box. And here's what I mean by that. So imagine you're running an ecological momentary assessment study where you're collecting data every single day, and you're looking at suicidal ideation. And you have a scale that goes from 0, no suicidal ideation, to 5, severe suicidal ideation. And so you have a participant who every single day for the first week puts a 0 down. They're happy as can be, no suicidal ideation, 0, 0, 0, 0. And then on the 8th day, they suddenly put a 5. So suddenly they go from 0 to 5, severe suicidal ideation. And if you're just collecting numeric data, you don't really know why that change happened. You just see this sudden crazy change. But if you had text data, you can ask what was going on in the participant's life, and it can tell you, oh, I lost my job, or oh, my girlfriend broke up with me. And then you get context for that numeric data. In addition, you can have a situation where two people answer a 3, so they have moderate suicidal ideation. But with the heterogeneity of depression, you know that depression appears differently in different people, so you don't know what that 3 means to each individual. What does it mean for this person and that person? And so text data can provide context for that. And it's not just text data, it can be audio and video that also provide additional semantic and contextual information. And in this way, you can also use this in tandem with classical psychometric principles for evaluating measurement quality. So as I'm trying to argue, text research is kind of the new wave of how we can do things to analyze psychological phenomena. And text researchers pursue the same goals as traditional psychometrics. We care about measuring constructs, explaining phenomena, making predictions. However, psychology has historically defined measurement as inherently numeric. Text challenges that assumption because it provides richer contextual information. Psychometric principles such as validity and expert agreement can still be applied to text models and embeddings. But there is this question of whether converting language into numeric vectors preserves the psychological meaning. And so luckily there's a study by Maruyama et al. In 2024 that of tweets that more advanced embedding methods can preserve psychological meaning. So as we transform this text data into numeric vectors, we still preserve the psychological meaning. So text embeddings allow us to study not only how much of a psychological construct is present, but also how language observations are organized. Traditional statistics summarize features such as means and correlations, but as we all know, different data sets can have similar summaries while forming very different shapes. Topological psychometrics therefore examines clusters, gaps, and other structures in the embedding space. Using TDA, we can test whether distinct psychosis language disturbances produce psychologically meaningful patterns that cannot be reduced to a single score. And again, this is generalizable. We can do this for any psychological phenomena. Okay, so the issue with doing text research is that we do not yet have easy access to large data sets that can be used in methods development. And I would also argue we may never have the appropriate text data sets because we need to control for specific features, and that's not so easy in text research. So that is the case here for finding a psychosis text data set that is appropriate for the research questions of TDA. So I generated the large data set of texts that contain a variety of psychosis language deficits, and I want to walk you through how that was done. So language deficits are not just a peripheral feature of psychosis. They're in the DSM-5 diagnostic criteria as formal thought disorder. While these deficits can affect a variety of aspects of language, to reach a clinical level, they must be severe enough to meaningfully impact communication rather than reflecting everyday lapses. So, for example, one deficit is perseveration, and that's just repeating of words or repeating of ideas. And I've probably done that in this presentation today, but I'm not doing it chronically, so it doesn't count as a disorder. But still, their severity is not static. It can vary depending on the stage of the illness. So these aspects make language deficits and psychosis a particularly good source for data for this project. So these are an example of deficits that I use in the project. So we have loose association, which means there's a lack of connection between the ideas as the participant is speaking. Again, perseveration, which is repetition of ideas and words. A peculiar word use, where you are using a word that has a definition, but it's not used in the correct way. And then confused references, where someone makes a reference, but it's unclear what's being referred to, who's being referred to. It's just unclear. Okay, so to get the text data out, you need to work on prompt engineering. So it is important to carefully craft a prompt which tells the LLM the relevant background, context, and instructions for your task. So I have another project where I look at generating depression data from the Beck Depression Inventory. So the relevant background for that project is the Beck Depression Inventory itself. I put the entire measure within the prompt. And then the context for that is I'm generating EMA data. So I tell the model, this is an EMA study. I want this many data points, etc. And then the instructions are limitations I put on the model for the kinds of texts that I want it to produce. So you could just have a model that just has background, context, and instructions, and that would be called zero-shot prompting. Or you can include examples of prompt response pairings, which would be few-shot prompting, which is what we're going to do today. So few-shot prompting has shown to better mitigate bias if the examples have minimal bias and care is taken with order. So the order in which you put your examples in does matter. So we need to generate data because there's no large open source data available for our few-shot prompting examples. So I created a curated data set of examples of linguistic deficits. So I found a bunch of articles that had examples of psychosis language that were labeled, and I used that to create a data set. So not all of them had been categorized. The ones that were categorized by the TLI and the CDI, which are measures of language deficits and psychosis. And for those that weren't, I read the definitions, looked at the examples, and then classified them according to the TLI or CDI. Okay, so what you do is you start with either that data science example or that suicidality text that I talked about in the example at the beginning of the presentation. And then you use the deficit names and deficit definitions and few-shot prompting of examples of those deficits. And what you output is one data science suicidality example that now contains psychosis features. So just to be clear, what you're doing is you're saying, okay, take this data science and introduce a psychosis language deficit to the data science example. And that's what's output. To generate the text with controlled language deficits, we use the Llama 3 8B instruction model. So that work in progress I mentioned earlier about generating depression text data also uses a similar method and uses the Llama 3 model, and it has been very successful. So the whole prompt includes a specific deficit we want to simulate, a definition of that deficit, and a data science or suicidality few-shot prompting example. And by conditioning the model on all of this information, we hope to generate text that systematically exhibit the targeted language deficits. And this gives us data we can assess both if we recover those deficits and find differences. So here's some example of the text that was generated. So first we have perseveration, which is an unwarranted repetition of ideas or themes. So just reviewing the text, we have jumping around like a balloon, floating away, up, 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 float away like a cloud forever, never, never, never. do nothing forever and ever and ever and ever. I'm just a balloon floating away, lost forever in the desert, alone, alone, alone. So you have that word repetition of up, alone, 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 and you have that idea of floating that keeps repeating. So the next example is weakening of goal. So there's a lack of drive in thinking and is manifest in the lack of normal elaboration of ideas, use of uninformative generalizations, and empty speech that conveys little information. So the text starts with talking about suicidality, but then it starts throwing in these random things that they don't elaborate on. Like trees not around, just like trees are not around. My hair is growing too much. I take bleach and put it in my hair in California. My roommate is from Chicago and goes to the junior college. So this method provides a numerically principled and stable method of generating text with specific properties. It can be used as a way of creating text for methods research. This opens the door for further work on text and topological psychometrics. Okay, so where are we going with this? So we have the background set up, we have the topological data analysis, we have the data generation. So where do we go? So here's some future research questions to use on the generated data. So using TDA, do differences in distances pick on differences in semantics or differences in deficit patterns? So differences in semantics would be differences between the different data science examples. So data science 1 and data science 2, which one, is there a difference between those? And differences in deficit patterns are comparing the specific deficits. So is perseveration different than peculiar word use? So this is the analysis plan. So we have semantic groups with 468 subsets with 500 iterations each. We have deficit groups with 8 subsets with 468 examples with 500 iterations each. The embedding models are Qwen3, Word2Vec, E5, and NV. The filtrations are Vittor's, Rips, and Check. The distances are Wasserstein with a P equals 1 and bottleneck. And then the comparisons would be between deficit groups, between semantic groups, and then deficit suicidality versus deficit data science. And that last comparison, there should be no difference there because what we want this to do is pick up on the deficits. So it shouldn't matter that one is talking about suicidality and one is talking about data science. If it's the same deficit, they should be close together. So the overall goals is we can discover the shapes of psychosis language trends and apply them to psychological problems like anomaly detection and early warning signs prediction. And though this may seem specific to psychosis, it is a general use method that can be applied across psychological phenomena, and this provides the basis for topological psychometrics. So thank you.